So now we're going to continue our journey down the digestive tract where we've been looking at the small intestine and large intestine and how they function in digestion. But we're going to divert our path a little bit and look at the liver, gallbladder, and pancreas and see how those accessory organs in the digestive system affect or help with digestion. So we'll start with the liver. Now we looked at the liver before when we did endocrine. We saw how the liver works in helping control blood glucose levels. So things like insulin, glucagon, cortisol, growth hormones, all those hormones affect blood glucose levels by acting on the liver or causing the liver to respond either by storing glucose as glycogen or releasing the glucose into circulation depending on the hormone. We'll see when we cover blood that there's also some hematological functioning that is regulating blood or what's in our blood. One thing it will do is engulf old or damaged red blood cells and process them. It will also be involved in synthesizing the plasma proteins. These are the proteins you find in blood that have all kinds of different functions, and a lot of it be associated to blood pressure regulation or blood clotting. So we'll talk about that when we cover blood. And then of course related to it is it cleans out our blood. That is, the liver will remove and store toxins, get it out of our blood so it doesn't hurt any of our tissues. That's also related then to its metabolic regulation in the sense that the liver is designed to process all the stuff we eat, the good stuff, the nutrients, as well as the toxins. And it extracts it and stores the excess nutrients or detoxifies those toxins, and then it can correct the deficiencies. So we'll see how it's going to basically kind of clean out our blood after the blood's left the intestines and absorbed all the stuff we ate. The last thing it does, related to digestion, of course, is produce bile. Now, bile is a mixture of stuff. Some of it's waste products, others of it's going to be needed for digestion. So bile includes water, ions. It's got stuff to dilute and buffer the chyme. Again, remember, it's going to be dumped into the duodenum right at the end of the stomach or beginning of the small intestine, and so we've got all that stomach acid that we've got to neutralize. So some of the ions like bicarbonates are going to help in buffering that acid from the stomach. It also has bilirubin. Now, bilirubin's a waste product of the breakdown of hemoglobin that we have in our blood. So when the liver processes the red blood cells, it's got to break down the hemoglobin, and bilirubin is what we got to get rid of. Now, also the bile is going to have some cholesterol in it, and then finally it's going to have bile salts. Now, these bile salts are important for digestion because they're going to help with fat digestion. So let's look at the structure of the liver in a sense related to its circulation. This is another portal system. We saw a portal system between the hypothalamus and anterior pituitary. Here's another portal system where, again, portal systems are just an added capillaries to the whole thing. So we have two sets of capillaries. So the idea here is you've got the small intestine where all the nutrients are absorbed into the blood. Now, all these nutrients and toxins, so junk that was in the food that we really don't want, all gets absorbed, and that ends up then circulating through the hepatic portal vein, coming from the intestines, the capillaries in those intestines, through the hepatic portal vein, and then entering the liver. In the liver, those blood vessels branch out to form capillaries again, and then the liver is going to process all that stuff that's in the blood that was absorbed through the small intestinal wall, and then process all that and get rid of the crud and store the excess and all that. Then those capillaries collect up, the blood exits the liver through the hepatic vein and finally into the inferior vena cava, so it goes back to your heart. Now, this pathway I just described doesn't have much oxygen in it because it just came from the small intestine. All the oxygen that was stored in the blood is going to be utilized by the small intestine. So the liver does need an oxygen-rich supply of blood, and it gets that through the hepatic artery. So blood leaving the heart that's rich in oxygen will then go to the hepatic, through the hepatic artery, and also enter the liver. And actually both of these supplies the blood that's oxygen rich and the blood that's oxygen poor but nutrient rich, will mix together in the liver in those, and then those capillaries will deliver the oxygen and the nutrients and the toxins in the liver for it to utilize or store or detoxify or whatever. And then all that blood again collects up in the hepatic vein and back to the heart. Okay. Now on a side trip over here, not part of the portal system, but keep in mind that the liver is going to make bile, and so the bile that it makes is going to go through what are called hepatic ducts, and that bile will then go through these ducts and finally enter the small intestine. Over here you can see kind of a diagram looking at it at the liver. So we have the portal vein here coming in, bringing blood in from the small intestine where all those nutrients are and the toxins. And then we've got the hepatic artery that came off of the aorta to deliver oxygen to the liver. Again, notice how they branch out. Again, all that blood mixes together, the liver processes all that stuff, and then the blood collects up in the hepatic vein, returning back to the heart. Now the liver histology is quite rich in capillaries. If you look here, if we break down the liver in microscopic level, you'd see that the liver is made up of a bunch of hexagon shapes called liver lobules. All the tan cells here are hepatocytes. Those are liver cells. And you can see over here, all the blue would be capillaries that came off of a branch of the hepatic portal vein. And then the red here is going to be a branch off the hepatic artery. So you can see the two will mix together, and then the blood exits through another vein called the central vein. And you can see that again down here on this slide as well. So here's the hepatic, a branch off the hepatic portal vein. Here's a branch off the hepatic artery. Again, those two will mix together, and then through these capillaries, and then exit out through the central vein. Now these capillaries are also called sinusoids. They're very porous, so they allows a lot of the stuff that's in that blood to move into the hepatocytes, which you can see are right along each side of the capillary. And so those hepatocytes can then process all that stuff that was in the blood. Then it will take some of that stuff and convert it into bile, and that bile will then transport through what are called bile canaliculi and then collect into bile ducts. Okay, so now circulation-wise, again, all the blood's going to end up going through the central vein, but notice the bile actually goes the other direction, not towards the middle, but towards the bile duct. Now those three tubes here, those three vessels, the bile duct, the portal vein, the hepatic artery, actually I said branches of each of those, make up what they call a portal triad. Another cell that you might see in here, they've got scattered, is Kupffer cells. These Kupffer cells are simply kind of a white blood cell in a sense. It's not really a white blood cell, but it has a similar function of white blood cells in that it looks around for nasty things it needs to get rid of, like bacteria or something. And so it will digest or eat those guys up to get rid of them, and so the liver can't get damaged. Now the bile, again, is the important part of this. This is where we want to look at what its functioning is. Now the bile function is to break down lipid droplets into little teeny pieces. So in other words, the bile salts take a big fat globule like this, and those bile salts will mix with it and then break that huge fat globule into a bunch of little teeny droplets. That way we increase the surface area of that fat, and therefore the digestive enzymes can get to those fat droplets better and be able to digest all that fat up. Okay, with a lot more surface area, you can get at the molecules making up those fat droplets easier. That process is called emulsification. All we're doing is, again, mixing fat droplets with bile salts to make them into smaller droplets. Okay, so we have better get the enzymes to it. Now remember, this is not a chemical digestive process. We're not chemically altering the fat droplets. All we're doing is making it into smaller bits. So this is more of a mechanical digestion that's involved. Now the bile will then, or the bile salts will then be recycled back to the liver through the ileum of the small intestines, so that the liver can just recycle the bile salts, put it back into the bile, and we use it all over again. Now the gallbladder's job is to store and concentrate bile. So you can see here, these are the ducts of the liver that come from the liver. So the right and left hepatic ducts that bring bile from the liver. That bile will travel through the common hepatic duct, and then through the common bile duct here, and then dump its contents in the duodenum. Notice also that this duct combines with the pancreatic duct before it actually dumps its stuff in the duodenum. At this end of the duct system, we have a thing called the hepatopancreatic sphincter. Now this hepatopancreatic sphincter is a sphincter muscle, and we can control its diameter, and so therefore we can control the ejection of the bile and even the pancreatic enzymes into the duodenum. So when you haven't eaten anything, then that sphincter is closed because there's not really any point in anything being dumped into it, so into the duodenum. And so, but we keep making bile, so the bile will just basically back up. It just kind of gets, blocked. This is closed down here, the sphincter is closed, and so we keep making bile, so it gets backed up, and then it will back up into the gallbladder. And so then the gallbladder is here to be able to store all of that extra bile. And then we can get when we eat, CCK is there to get the gallbladder to contract, and then that will push the bile into the duodenum. And of course the sphincter is also relaxed while we're eating as well. Now, one of the problems associated with the gallbladder is the gallstones. Now gallstones are just basically little stones that are made up of a lot of cholesterol, and they happen when we get prolonged storage of the bile in the gallbladder, and we have too much cholesterol or too little bile salts. There's an imbalance in the relationship between the two that results in the formation of these gallstones. Now this can be very painful. Now most people don't have this extreme. I just thought this was amazing how many gallstones were in this poor guy's or girl's gallbladder. Here's a sonogram looking at it. Looked like little peas in a pot, if you ask me. But anyway, it is extremely painful, and so and it can cause what's called obstructive jaundice. Now, obstructive jaundice means basically you're obstructing the pathway for that bile to exit. So if I go back a slide, if I have a gallstone sitting here in the common bile duct, then it's the bile exiting out the duodenum is being obstructed, so the bile is going to back up and actually back up into the liver. And remember, one of the components of bile is bilirubin, and the bilirubin then will end up going into circulation. If the liver can't get rid of the bilirubin, it's just going to stay in the blood associated with the liver and then circulate through us. That bilirubin then ends up diffusing into our skin, and it turns our skin yellow. That's the jaundice. So one of the things we can see with gallstones is we get this obstructive jaundice. So to fix this, let's just take the gallbladder out. You do a cholecystectomy, remove the gallbladder. And people can function fine without their gallbladder. You don't absolutely need it. You may have a little hard time digesting fat, so you want to stay away from fatty foods because the bile salts are going to help us with that. Remember, that's going to break those fat droplets down. So instead, I'll go back again, if you don't have a gallbladder here, basically what you're going to do is have the bile just slowly go out, and the sphincter opens up and empties, and it's just fine. But it's going to more or less think of it kind of as a drip instead of getting to be stored here and then have a big, huge amount of bile added when we're eating. You're just going to have kind of a constant drip. So you're going to have a little harder time digesting fat. Your fecal material will be a little on the fattier side, but otherwise you're going to be fine. Now, gallbladder secretions are going to be regulated through hormones. When not eating again, that hepatopancreatic sphincter is closed, so the bile backs up into that gallbladder again. But if we start with when the fatty foods enter the duodenum, remember we get cholecystokinin and secretin released from the duodenal wall, from those enteroendocrine cells of the small intestine. So those guys go into circulation. The cholecystokinin will cause the gallbladder to contract. The secretin will get the liver to make more more bile, and even the vagus nerve can stimulate and cause contractions of the gallbladder. So parasympathetic input can get the gallbladder to contract. So between CCK and vagal impact, we can get the gallbladder to contract. Secretin will get the gallbladder to make more bile, and all of that will contribute to moving bile into your small intestine, and therefore the bile salts will help with the fat digestion, and then they just get reabsorbed back into blood, and the liver will take those bile salts and reprocess them. All right, so let's look at the pancreas now and see what it does. Now, the pancreas, remember, has kind of a dual duty. It's an exocrine function. The cells called pancreatic acini cells, which you can see down here, are all these little cells here. So we have a lot more acini cells than we do those islet cells that we see for endocrine function. Now, we've already talked about endocrine function, making the glucagon and insulin. So now we're just going to concentrate on exocrine function. The enzymes are made in those acini cells, and then the epithelial cells lining the ducts that feed off of those acini cells, then make water and ions, including bicarbonates, to help neutralize the chyme. And all that's going to mix together and then travel down the pancreatic duct, combines with the common bile duct, and empties into the duodenum here. Okay? Now, all the pancreatic secretions are coming from either the epithelial cells or the acini cells. So again, the epithelial cells, they're making the bicarbonates to neutralize the stomach acid, and the acini cells are making the enzymes. And we have lots of different enzymes. We've got pancreatic carbohydrases, which are an amylase. So pancreatic amylase breaks down carbohydrates. Pancreatic lipases break down the lipids. The pancreatic proteases break down the proteins. Now, like pepsin and pepsinogen, pancreatic proteases have to be secreted in an inactive form. Again, if we secrete these protein enzymes or proteases in an active form, they're going to digest the proteins in the duct on the way to the small intestine, and that of course is no good. That would destroy your pancreas, so we don't want that. So they need to be activated in the small intestine. And they're activated by an enzyme within the small intestine. And so the inactive forms are here on the left side of the equation, or equal sign. The right side is the active form. So trypsinogen gets converted to trypsin. Chymotrypsinogen gets converted to chymotrypsin. Proelastase gets converted to elastase. And those all three are enzymes to digest protein. Now, as far as regulation of pancreatic secretions, in this case, what we're doing is, again, food arriving in the duodenum. We get release, again, of those hormones because of the food there. So we get cholecystokinin again and secretin released. Those guys enter blood circulation. When they reach the pancreas, the cholecystokinin induces secretion of the enzyme. Secretin gets the bicarbonates from the epithelial cells to be secreted, and therefore all of those secretions then enter into the duodenum where they do their job. Okay. Now also the parasympathetic system through the vagal nerve can also get release of pancreatic juices. And again, remember in the cephalic and gastric phases of gastric regulation, we're prepping the intestines to get ready for the food to come. So we want to include the enzymes and bicarbonates that the pancreas has to get the intestines again ready to go. All right, so that ends our little side trip to the liver, pancreas, and gallbladder. And so in the next video, we'll pick up on our trip down the digestive tract with the large intestine.